Today we'll talk about something called Intel ME. So let's see what it is. I'll talk about what it is on high level. I'll talk about some low-level details. I'll describe the security of ME and what attacks are possible on it, and some other components. Anyway, if you're interested, if you care about who I am and what I do, you can read it later on the slides. So let's talk about ME. ME stands for Management Engine or Manageability Engine. Intel cannot decide which one it is. So this is dedicated microcontroller which is embedded in all recent Intel platforms. So it is embedded in the chipset. So you have on your motherboard, you have usually the processor, and then you have some supporting chips from Intel. So ME is usually in one of those supporting chips. It's part of the chipset. So it's a separate microcontroller. It's not Intel x86, but it's usually some other core. In the first versions, when Intel just introduced it, it was intended for management, as obvious from the name. So they put it in the network card. One of the, I think it was codenamed Tekoa. And later they moved it, because it was more convenient, they moved it into the chipset. So this microcontroller, it needs some code to run as a normal processor. And so this code is stored in the same flash chip as the code for your BIOS. However, the controller itself is completely independent from the main CPU. So for example, it can be active when your main OS is shut down, or you pressed the power button and your computer seems to be off, but this microcontroller can be still active, can still communicate with the network, as long as it's connected to the power. It has a couple of volts of energy to work. So it has a dedicated connection to the network interface. So it can talk to the network bypassing your CPU, bypassing your OS. So if you run Wireshark, for example, on your main OS, you will not see traffic from this microcontroller. So here's a diagram from Intel's documentation. And you can see we have the CPU on the left. Then we have graphics and memory controller hub, which is part of the chipset. And this microcontroller is placed inside of it. And it has different components. It runs RTOS called ThreadX. And then it has several different software components that are responsible for different management tasks. And it has interfaces to the host to talk to the host OS. It has interfaces to the network card for out-of-band communications with the rest of the network, and some other peripherals, and so on. So how does ME communicate with the outer world? So it can communicate with host OS, so with the software running on your main CPU. And for this, it uses a special interface, PCI-based interface called Host Embedded Control Interface, or later it got renamed into Management Engine Interface. And this allows drivers on your main CPU to talk to this management engine and to send it some commands and communicate with it. However, it can also communicate by passing the main CPU. It can communicate directly using the network card, the dedicated network card interface, to communicate with the outer world or the network. And that interface over the network is for some reason SOAP-based. It can be using HTTP or HTTPS, depending on what you prefer. So a bit more about what is inside this management engine. So one of the biggest components, well, it's not just one component, it's a combination of components called active management technology. This allows, for example, the system administrators in a big company to remotely configure, administer repair the workstations. For example, they can remotely reboot workstations. They can boot remotely using the IDE emulation and reinstall the software and so on. System defense, you can add some low-level rules on the network packets, matching, for example, some ports or some packet sizes or whatever. And this will be checked on the lowest level in the network card itself. So this can act as kind of a hardware firewall. Yes, IDE redirection, as I mentioned, you can boot remotely the workstations. You can pass an ISO image, for example, and the target computer, the workstation, will see it as if it's attached to the computer itself, the CD drive, for example, or hard drive. And you can boot the OS, or you can boot some recovery environment and install it on that computer without coming over all that, 10 floors to it. So this is very convenient, of course, for the administrators. And that's why Intel implemented it. Identity protection. In recent versions, they started adding the OTP functionality. So some programs and some sites can use this one-time password for extra authentication, so as two-factor authentication. Protect transaction display. It allows ME to show the picture directly on the monitor bypassing the OS. So the OS will not be able to intercept this image, will not, for example, the screen monitoring software will not see this image, and so you can use it for secure PIN entry, for example. Anti-theft, Intel has an anti-theft solution, and if you activate your ME using this feature, it can check periodically with the anti-theft server, and if it fails to check in after several tries, it may lock the PC, and you cannot boot it anymore, or it will reset every 30 minutes, and you will have to unlock it by calling the provider, and they will provide you with the recovery code, of course, if it's still in your hands. But the thieves, in theory, will not be able to recover it because it will be blocked on the lowest level. Even reinstalling the OS, reflashing the BIOS will not help. So in some versions, you could also signal that the PC is stolen, and on the next check-in it would be disabled. Or you could also maybe send the so-called poison pill over 3G connections. It was available in some laptops. Now this functionality is deprecated. They don't use it anymore, but at some point it was available, so you could kind of send in this, well, not you, but the call center could send this poisoned SMS to the computer and it would be disabled. And in some versions, you could also notify the encryption software on the host OS that the computer has been stalled, so it could erase the encryption password. So that was a bit high-level overview. So, and then I was of course interested. This was all high-level stuff you could read in white papers and patents, but I was of course interested in how it works, how it's all implemented, what is inside. So there was some information in white papers and patents. For example, they mentioned in a couple of places that the CPU core is an ARC processor, and that it's running ThreadX RTOS, but not much other information was available. So I looked at some of the drivers and software available from the Intel. So all chipsets that have this management engine enabled, the Intel provides drivers that talk to it, and some extra utilities that do management tasks. They also provide the SDK for enterprises so that you can program utilities that talk to various machines and do management tasks with them. So that was useful source of information. You could glean some low-level details from those SDKs. Linux drivers, they also provide Linux drivers for ME. And of course, being Linux, they have to provide full sources for those drivers. So this is still the host side, not the ME side. So you don't get much information about the internals of ME itself, but you can at least see how the communication is being performed, and some information is available in this way. Coreboot, the open source BIOS alternative, it also has support for ME on some chipsets. So you could see the low-level communications with ME. BIOS updates. So as I mentioned, the ME management engine shares the flash space with the BIOS. So it has the firmware is stored on the same chip as the BIOS firmware. So if you download some BIOS updates for some motherboards that have ME, you often find the ME firmware embedded in this update. So even though usually it's not updatable using the normal BIOS updates, you can still have the ME firmware in them. And in some cases, many manufacturers, especially Lenovo or HP, they release separate ME firmware updates, and you can download those and analyze them. So there is also something called ME firmware kit. This is a bundle of software and firmware that Intel distributes to manufacturers that make motherboards so that they can prepare the BIOS and it contains informations, various low-level tools, and so on. So normally these firmware kits are not supposed to be shared with the end users. However, many manufacturers are lazy, so they just take whatever Intel sends them and they put it online as a driver for ME. So if you download that driver, you get all the Intel tools, all the fancy Intel confidential PDFs and so on. So that's quite useful. So you just, if you know some keywords to search for, you can find many of those tools and many of those documentation available. So that's useful. And then in the end of last year, Intel released something called firmware support package. So they decided to be more open, and they released this package for the people who make their own BIOSes for Intel chipsets. For example, the people making embedded boards. So this contains the low-level initialization code from Intel, so that you can take this binary blob, run it, and then it will initialize all the low-level stuff, and then you can continue with your booting or whatever you do in your bootloader. So this was freely available from Intel side, and one of the packages, I don't know if they did it by accident or it was intentional, they actually put this ME firmware kit complete, and they even didn't remove the Intel confidential markings. So yeah, it was useful. I think right now they replaced the package, but you can still find the old one on the Intel site if you know where to look for. So this is another source of information. So I looked at all those sources, I reversed a lot of binaries, I read a lot of documentations, and here I summarize a bit of what I learned. So the BIOS firmware and ME firmware, they are stored together on the flash chip. Usually it's SPI flash chip. And it contains firmware for BIOS, for Intel, for ME, for Ethernet card. And for security purposes, Intel decided so that, for example, the BIOS should not have access to the Intel ME region because it may have some sensitive information, various encryption keys or whatever. So they use so-called flash descriptor to signal the chipset which parts of the system has access to the various part of the flash image. So the flash image begins it's the bottom, begins with this flash descriptor, which has different flags that tell the chipset, okay, so the BIOS component, so the host chip, the main chip, has access to the BIOS region, but not to the ME region. And the ME chip has access to the ME region, and maybe it also has access to the BIOS region, and so on. So this way, they can have hardware-enforced access checks to limit access. And so this way, the flash space is partitioned in several regions. So there is BIOS region, which is usually at the end of the chip, then Intel ME region, then maybe the Ethernet region. Some of them may be there, maybe not. So we're of course interested in the ME region. So even if you cannot read it from the host chip, usually, as I said, you can extract it from the BIOS updates or from the separate firmware updates. So this ME region, what does it contain? It's not monolithic. It's not like the BIOS region, which is usually just a bunch of code. The ME region contains itself in turn of several partitions. So it starts with a partition table, and that partition table has a start and 4-character code of the partition and the type of the partition. So here's a typical layout of an ME region. So it begins with the partition table, then it starts with partitions. For example, this is, I think, firmware fixed offset variables that control various parameters of the ME. Then EFS flash file system that stores the various runtime information of the ME. And then we have the code partitions, which contain the actual firmware code which is executed on the chip. So these code partitions, they again split into several parts. So they begin with the so-called manifest header. And this header has various flags and the headers of the modules that is contained in this code partition. So the code partition can contain several code modules in turn. And this whole header is actually signed with RSA. And in the header you have the public key and signature, so that the boot ROM of the ME can hash the whole header, except the key and the signature, and verifies that it matches. Try to decrypt with the public key and try to decrypt the signature with the public key and see that it matches. And the hash of this public key is stored in the boot ROM, so you cannot just resign it with your own public key and replace the public key in the header. It will not work. So Intel did a pretty good job here, and the code is protected. You cannot modify the code, and because the signature is verified. So I looked at many different firmwares, and it seems from what I saw, they had roughly 3 generations of the hardware of this ME. The first versions, up to version 5 or so, were using the Arc Tangent A4, possibly A4 chip, and it was using the 32-bit Arc instruction set, the old instruction set. And they were using the LZMA compression or no compression for the code modules. The second, I call the second generation, I don't know what Intel calls it. Starting from version 6, they switched to another Arc processor that employs the Arc Compact instruction set. And this is Arc Compact, it's somewhat similar to SAMB instruction set RAM because it can have short instructions, 16-bit instructions, so it saves space, I guess, code space. Maybe that's why they switched. And in addition to LZMA, they can use also the Huffman compression, which is implemented in the hardware. I will talk a bit more about it later. And just last year, they released the Bay Trail system on chip, and it has also embedded ME, except they don't call it ME, they call it TXE. And it uses, for some strange reason, Spark architecture instead of Arc. But luckily they removed the Huffman and use only LZMA, so we can analyze all code. I will talk about it later. Most of my investigation covers the second generation, so version 7 or 8 or 9 and so. So I will talk about it. Some of the modules, so as I mentioned, the code partitions in turn themselves contain code modules, and they have names. And the names are not really described anywhere, but you can kind of figure out the meaning from some of them. For example, a module called BUP, which is the first one being executed, apparently means bring up. And it is responsible for initializing hardware, configuring hardware, and so on, various initialization tasks. Then there is a kernel, contains the scheduler, and various low-level APIs that other modules use, so the common APIs for other modules. The policy modules perform some initialization, some extra configuration, and so on. Hostcom handles communication with the host over the host embedded control interface. Capability license service, a couple of years ago, Intel tried this thing with software upgradable processors. So you can buy a scratch card from Intel and use their software to enter some codes, and your processor would get a bit more cache or a bit more threads. I don't remember what exactly. I think a bit more frequency. So I suspect this functionality was implemented actually in the ME and using this module. So yeah. TDT apparently means theft deterrence technology, so the internal name for Intel anti-theft. Protected audio-video path, which is used for the secure PN entries that I mentioned, and possibly for some other applications. JOM, I don't know what it stands for. I think maybe Java Object Model or something. It implements the dynamic application loader. I will talk about it later. And in later chips, in latest versions, they also moved the TPM functionality into ME, and they have the FTPM module which implements the firmware TPM. So now you don't have to use a separate chip for your TPM, but you can use the one that is built in ME. Some of the difficulties that I encountered when analyzing this firmware, apparently to save flash space, some of the most common functions are implemented in ROM, on the on-chip ROM. And so you analyze the code, and then you see the pointer which goes nowhere, a jump or a call that goes nowhere. And apparently it goes to the boot ROM, which of course I don't have access to. I have only the updatable part of the firmware. And it was a bit difficult. Of course, after some point, you see the call used here, there, you see the parameters, you see the surrounding code, so we can kind of guess, okay, so this looks like a mem set, this looks like a mem copy, this looks like a string copy. So some of them we can guess, but still, it was a bit difficult to not have all the code. So, yeah, it was a bit of a pain to work on this. However, I came across a firmware image for one of the boards, and it has an interesting partition that I haven't seen before called ROM-B. So usually we have partitions, as I said before, EFFS, FOVD, and TPR, and so on. But ROM-B I haven't seen before. So I looked at it, and apparently it contains just raw code. And it's not a standard code partition because it doesn't have the manifest header. It's not signed. So how it is used by the chip? So I looked for some keywords, and I finally found some information in Intel documentation that ROM-B apparently stands for ROM bypass. And ROM bypass allows Intel to release the so-called, so to speak, firmware upgrades for the boot ROM on the chips. So when they release the new chipsets, the new hardware, they distribute to the manufacturers to start working on their own boards. And of course, this is very early silicon. It contains bugs, and it may also contain bugs in this boot ROM of the ME. So they allow for this early silicon, non-pre-release, they allow you to kind of flip a bit and tell, okay, don't use the boot ROM, but boot from the flash directly from this ROM B partition. Yeah, I was kind of happy that I found it. I tried immediately to use it on some boards that I have, but of course it does not work on the consumer hardware. It just ignores this bit. It does not use the image from the flash. So if you have access to some some OEM boards from Intel, it might work. So it may help you. But unfortunately, I don't have. I have just consumer boards. So this did not help me to run my own code on ME. However, it did help me to analyze the code that usually is present in the boot ROM. So if this option is enabled, as I said, the chip does not use the boot ROM, but it jumps directly to the ME region, and the ME region happens to have a jump instruction in the beginning, just before the partition table, and so this jump goes to the ROM B partition and starts executing the code. So I looked at that code, and I saw basically all the tasks that I usually performed by the boot ROM. So for example, I could see all those common C functions, memcopy, memset, and so on. I could see the implementation of the threadx RTOS routines, low-level access API. I also could see the functions that perform signature checking, and so on. So I could see that this code, for example, takes the FPTR partition, loads the bring up module, and after verifying the signature, jumps to it. Yes, unfortunately, in the modules that I was looking at, this bring up and kernel modules, they employ Huffman compression, which is implemented in hardware, so I could not figure out how to decompress it. So I did not have, I still did not have all the code. So I had the code of boot ROM, but not the code of the kernel and the bring up. So that was a bit disappointing again. Now, sorry?
Where is this dictionary supposed to sit?
Where is the dictionary supposed to be? I think it's just kind of hard-coded, well, not hard-coded, but in the chip itself, I think it's implemented in hardware. There is some kind of hardware decompression module that just, it says, okay, you read from this address and it decompresses on the fly, and the chip core sees already decompressed instructions. So I could not find any signs of a dictionary. All the parts of the firmware were accounted for. So no, the dictionary is just not there. I think it's embedded in the chip. So after analyzing and also by reading some documentation, I could see the various security features that were implemented by Intel. One of the major features, of course, is the code signing. All code which is running on ME. I think all code, yes, except the boot ROM, which you cannot access, which you cannot modify. So all this code is signed with RSA, and the boot ROM checks the signature before loading and running it. And this code is signed by Intel using their private key that they keep secret, of course. And the public key is stored in the firmware header. But as I said, once again, you cannot just replace this public key because the hash of the public key is still checked by the boot ROM. So they just don't store the public key in the boot ROM itself to save space because it's 2 kilobytes. So they store only the hashes of public keys that can be used for signing. So this is one of the features. The second security feature is that, in fact, the ME shares with the main CPU not just the flash chip, but it also shares some RAM with the main CPU. Because the RAM inside the ME is somewhat small, and I think it's a bit low speed, so it also has an option of utilizing some of the RAM of the host CPU. So it can carve out a bit of space in your main RAM. Usually it's around 16 megabytes, so it's pretty small. So how it is done? So first, when it boots, it of of course, boots using its own RAM, so small amount, a couple of kilobytes, I think. But then it waits for the BIOS to boot and for the main CPU to boot, and waits for the communication from the BIOS. So what the BIOS does, it checks the registers that ME sets to check how much space ME needs. BIOS allocates this chunk of memory at the end of your RAM, and then it programs into the chipset registers this address and length of this region, and then it sets the log bit. So once the log bit is set, the host CPU cannot access it anymore. So this is enforced by the chipset, not by the main CPU. So that's why the main CPU cannot access this chunk of memory anymore. So once this log bit is set, once the memory is allocated for the ME, it unpacks its own modules into that big RAM, big fast RAM, and starts executing from it. So as I said, host CPU cannot access it. However, there was a bug in the memory remapping functionality of the chipset, and in 2009, Invisible Things Lab found a way to kind of hijack this memory remapping to get access to the ME region and to get read-write access to it from the host CPU. And they used it to inject their own code into the ME and to do some things. And then later, researchers from Germany, they used this attack to implement the keyloggers. There was a presentation, for example, on CCC at CCC last year about implementing keylogger. Unfortunately, this vulnerability has been fixed in the following chipsets. So in all the modern chipsets, you cannot access ME memory using this trick. So I tried to look for other ways. So as I mentioned, I could not decompress some of the modules because they use Huffman compression, but quite possibly when it's unpacked into the RAM, it's in unpacked form. So maybe if I dump that memory region, I could look at the code of ME. So I thought about using various tricks. So the first, of course, is the most obvious. Because this log bit is set by the BIOS. What if we don't set this log bit? We just say, okay, here's your memory range, but I don't set the log bit, but still try to continue. So I reversed the memory initialization. It was a big chunk of code. Found finally the place where the log bit is set. Patch it out. Update all the checksums with UEFI. It's a pain. Refresh the firmware, reboot, and I get black screen. It just starts up the fan, then shuts down, starts the fan, shuts down. So it was basically the bricked board. Luckily, I had a similar board, so I could do the hot swap, flash hot swap trick, and reflash the bad BIOS and bring back the board. So this didn't work out. So next I tried the cold boot attack. So I have the 2 memory sticks in my board, and when the ME requests the memory range from the BIOS, it's allocated, of course, in only one of them, and its range is not accessible by the CPU. So what I thought about was, okay, I boot it once, the ME unpacks into this memory, everything is fine. Then I quickly turn it off, swap the 2 memory sticks, and boot it again. And if I'm lucky, the memory contents still remains in the other memory stick, and so I can dump it. So I tried it. I tried memory many times, just garbage. So I tried the lower speed memory. I thought maybe okay, it decays too quickly. I tried the freezing spray instead of just the compressed air. Didn't work. So eventually I discovered that because I used DDR3 and not DDR2, they implemented a feature called scrambling to reduce the signal interference on the address lines and data lines. They apply some pseudo-random scrambling so that they had better distribution of signals and there is less interference between the signals. And so this scrambling apparently because it depends on the address and on the actual data which is sent over. So if you swap the sticks, the address changes and the scrambling being applied is different, so it doesn't work. So that was disappointing. Then I had an idea to not use a different memory stick, but use the same memory stick. So, as I mentioned, the size of the region is set in the ME, the size of the region to use. And in fact, it's one of the fields in the partition table. And this partition table is not signed; it's just protected by the checksum. So I can change this field and reflash the ME. Well, I defeated the reflashing protection in other ways, doesn't matter. So what I thought, okay, usually the ME requests 16 megabytes, so what I do, I increase this size to 30 megabytes. I reboot, the BIOS allocates 30 megabytes, but the ME uses only 16 megabytes. So it puts its code in there. Then I reflash the firmware with 16 megabytes. So BIOS allocates only 16 megabytes. But the old 16 megabytes is now unlocked, and I can access it and I can dump it. So I tried this trick again several times, but unfortunately it again didn't work out, apparently, because of the different scrambling seed is used for every reboot. For every boot. So once I reboot, the scrambling seed is regenerated, and so of course when I read the memory, because of the scrambling, I get garbage. So I thought, okay, how do maybe it's possible to turn off the scrambling? And apparently it is possible. In some server boards, this setting is available in the BIOS. You can turn off this scrambling. And I looked at my BIOS. I looked at the names of the strings available in it. Apparently, the setting is present in the BIOS, but it's just hidden using different flags. So I could still find out which bits, which byte in the setup variable it's controlled by, and I could change it using just the low-level EFI variable editing tool. So I don't expand on it because it's not important how it's done. You can check how I did similar thing in my previous presentation. So I turned off scrambling. I disabled scrambling generation, so it was using memory without scrambling, but unfortunately, it still didn't work for some reason. I'm not completely sure why. I think it's because of the memory training. The training routines, they destructively test memory when they initialize it. So I think maybe if I patch it out, maybe I will be able to. But so far, I was not able to dump it. So I have some other ideas which I'm not ready to share yet. If I'm lucky, I will be able to dump this memory finally to analyze it, but so far I had no luck. So I looked at some other approaches. So what can I do to analyze the missing code? And I found something else called server platform services. So on server boards, on Intel server boards, ME is also present, and it runs a different kind of firmware, which is called the SPS server platform services, and it contains a limited set of modules. So it does not have all the consumer stuff like AMT or whatever, the TPM stuff, but it does have bring up and kernel modules. So, and great news is that bring up module is not compressed, so I can just look at this code. And if I look at the kernel mode, it's also supposedly Huffman compressed. However, all blocks have 0 compression set, so they're stored without compression in fact. So I could finally, well, I had to stitch the kernel module out of the blocks because they use weird addressing for this Huffman compression. But I figured it out, and I could reconstruct the kernel module, and I could look finally at it and see what's inside. So it's not completely the same as in desktop versions. However, it's still mostly many code, many routines are the same, so it's a big help. So I could look at it. And using this information, I finally looked at some of the modules that were basically using some APIs, some routines which I had no access to. So one of these, for example, I looked at is called JOM. I think it's Java Object Model or something, which appeared in the ME7.1. And why I looked at it? Because it implements very interesting functionality. It allows you to upload applets into ME and execute them at runtime. So not just run the code which is already there, which is in firmware, but you can run additional code. And for example, they implement the identity protection technology, this one-time password thing, using those applets. And in theory, it could allow for running your custom code on ME without reflashing, without having to find hooks into memory. So let's see what we have inside. Of course, the best thing to start with is run the strings on the binary. And if you run, we have some interesting strings like Java lang out of memory error, starting VM server, could not allocate instance of. So yeah, Java, of course, it's a very big hint, and also the class names. So yeah, apparently it's something like Java inside. So yeah, I looked at the code. Yes, it does seem it's something similar to Java. And in fact, if I looked at some of the files installed by the Intel drivers, there is a file which is XML with base 64 encoded blob. And once I decode that blob, I get very similar manifest as used in the firmware itself. And this manifest has a signature Jeff, which is again mentioned in one of the strings. So and you look at those strings in that Jeff chunk, and it's mostly Java, like array, bytes, whatever. So it seems it's not Java class format, but it's something similar apparently. Unfortunately, the opcodes are different from the standard Java. So I had to I spent quite a lot of time looking at this JOM module to see how what do opcodes mean, what it does with each opcode, how it parses this file. It's pretty complicated file format, so I spent quite a lot of time. I thought it's custom format because I never heard of something different to Java class files. However, I came across this interesting string in the module, invalid constant offset in SLDC instruction. The standard Java does not have SLDC instruction. So what is this instruction? Let's see if Google knows anything. And in fact, I looked at, I searched SLDC opcode Java, and I actually got some hints for something called Jeff. So apparently I spent a couple of months in vain, and the Jeff format is a standard. However, it's pretty old standard. It was proposed in 2001 by something called J Consortium. They tried to push some standards in alternative to Sun, I think, at that point. And in fact, they managed to even to, in those few years that they were active, they managed actually to push it as an ISO standard. So ISO standard, of course, you have to pay big bucks to download them, but you can find some drafts still around. And you can read the implementation, the description of the format and everything. So apparently it was intended for embedded applications. So what they do, they combine several classes into one, so like a jar, but it's not, jar is basically just a zip of separate classes, but this one is a bit more. They, for example, combine all the constant strings into a single pool, which reduces the size quite a bit. And they also kind of pre-link this file by replacing references between the classes by indexes. So it's optimized for embedded, so it's supposed to be runnable just like this without a separate linking step. So you can just have your VM to look up those indexes and jump to different classes inside the same file. So for example, they even have some references to constant strings as file offsets instead of indexes in the constant pool and so on. So it's a pretty nice format. Apparently, it's still used by some point of sales, I think, software things, but not much besides that. But it was used also on this Intel ME. So finally, I had the full description of the file format. I had the description of all opcodes, and apparently it also has an ability to call native implementation by some index. Some native methods can be implemented. So I made the assembler in Python. Yes, they in fact had at one point the utility to work with this file format. Unfortunately, the site is long gone, and the Internet Archive did not keep a copy of that utility, so I had to implement my own. And so I made this utility and looked at the implementation. I looked at how it's done. So they don't use obfuscation, which is thanks Intel. In fact, most of the Java basic classes like Java string, Java array, they implemented bytecode. So only the lowest level things which need to allocate memory and access some memory are implemented in native. So you have access to almost the whole runtime. So they provide classes for cryptography, for UI elements, for the secure pin entry apparently. You can access the flash, you can store some variable and load some variables. And they also provide this interface for those loadable applets. So here's a fragment of output from my tool. So you can see the standard class. It has some member variables, it has some methods, and so on. So apparently, to implement an applet, you can do it like this. There is a onInit method, onClose method, and invoke command. And so you can just handle some commands sent by the host and do your thing. Unfortunately, even if I make the translator back from Java to this Jeff class, I cannot run them inside the ME because they are signed. As I mentioned, they have this manifest header, which is again signed by the Intel private key, and they verified before running, so you cannot replace them with your custom code. However, the protocol which communicates with the host is pretty complicated because there are buffers involved and so on. So let's see what is this protocol. So how does the host OS communicates with those applets and uploads those applets? So Intel has some DLLs installed with the drivers, which provides various high-level APIs, and those APIs again are not obfuscated. They have very nice readable names, so you can just look at the implementation and see what they do. They use a service. Well, it's only available on Windows for the moment. So they use a Windows service which handles communication with the hardware. And the DLLs communicate with the service using COM or TCP/IP. The service serializes requests, wraps them into packets, and sends them over to the ME. On the ME side, they received. They are handled over to the JOM module. JOM module decides which applet it is intended for and passes to the applet. Applet implements this onCommand method, handles, and maybe sends some reply to the host. And it goes back. It wraps again in the packet, sent back to the host, and the service passes it to the DLL. So it's quite a complicated chain. You have several layers, and of course, whenever you have buffers involved, you have potential for buffer overflows. So far, I haven't found any, but I keep looking, and maybe I can find something, because it's very promising venue, because I could just send commands from my host. I don't have to reflash, I don't have to reboot, nor anything. I don't have to write my own BIOS or whatever. So I keep looking at it. So far, I had no success, but it's very promising. So a bit more about this internal of this JOM module. So apparently they implement a trusted execution environment, and its implementation provided by Trusted Logic Mobility, which is now Trustonic. ARM also one of the participants, and it's called Trusted Foundations. Yeah, they provide various abstractions and stuff. And the interesting thing about this trusted foundation software is that it's used in several smartphones as well. I think some Asus transformer or whatever, or something like that. So then it's implemented using ARM Trust Zone. So it's ARM code, and ARM code, if you find this implementation, can just disassemble nicely and even decompile. So it's much more convenient. And drivers also available because those phones run Linux, Android, and they have to communicate with the hardware with those trusted foundation. And so the drivers are available, and you can see some of the protocol used for the communication. It's not exactly the same because on Trust Zone they use shared memory, but on ME they cannot use shared memory because they only talk over this management interface, so it's all serialized. However, there are many common parts, so it's quite useful. Another helper is there is a specification released by the Global Platform Association. And this specification, again, is not completely the same as what is implemented in this Trusted Foundation software, but there is a big overlap. So it's also useful to see how things work and so on. So I have to wrap up. So I still don't have the rootkit. Yeah, my first presentation on it was optimistically called "Rootkit in your laptop." So far, no rootkit yet. However, I get a more and more complete picture. So I have the code of basically all the parts of the ME. I declare all the APIs. Yes, I made this dumper to look at the applets, and because of this, I implement the ARC module for IDA, which was useful for a couple of other people as well. And what's next? So I keep looking at the dynamic application loader. Maybe try to implement my own client for this IPT thing, so that I can try to fuzz it. Yeah, EFFS, the file system on the flash chip for the storage of the ME state. It contains some variables, which some of them are protected against tampering, but many of them not. So maybe if you change it, you can trigger something in the ME. It's a bit complicated because it has to support flash wire leveling, so it's not a simple file system, but it's a point. Yes, half-mount compression I mentioned. As I said, apparently the dictionary is hard-coded in Silicon. You cannot access it. However, with some people from SmartJustTech site, we managed to uncover, due to help some other people who managed to dump, I don't know how, managed to dump the version 6, so we could recover some of the dictionary. However, the version 7 and future and further versions, they use a different dictionary, so we cannot reuse this work, unfortunately, for the current versions of ME. However, we have some progress. Yes, looking at the protocols is another target. BIOS reverse engineering should be useful. Simulation and fuzzing. I still haven't done it, but it should be possible to simulate this firmware. And I mentioned briefly something new I discovered just a couple of months ago. The new atom-based system on chip released by Intel called Bay Trail. They embedded everything in one chip, so the memory controllers, everything in one chip, and the ME itself is also embedded in this chip. But they renamed it. They don't call it ME now. They called it TXE. Apparently means Trusted Execution Engine. And they use Spark core for some reason. Not sure why they switched away from Arc. Maybe the Arc is asking too much money for their license. I don't know. And they don't use half-mount compression, luckily. So only LZMA. So all the code except the boot ROM is available. So I can look at the kernel code. I can look at the bring up code. So this is very nice. But of course, Spark is a bit of pain as they use delay slots and stuff. Arc is much nicer. But however, there are more tools for Spark. So there are emulators available. So maybe I can make some emulator for this firmware and look at this Spark code. So I just started on it. Didn't do much with Spark yet, but it's very promising. So there are various links you can look at. You can download slides later. Yeah, many people did different also investigations on this, and it was useful also for me. And yeah, a bit of our time, but thank you for your attention.